So welcome you all. Uh, my intention in this video is to give you some beautiful understanding about how we can do an integration or differentiation, mainly focus on integration through the operational amplifier, and by simulating, see some fun facts about how mathematics meets these analog systems and the some kind of applications that we can apply these rules like BID systems, proportional integration and differentiation. So let's get started with some basic things about op-amps. I think you have some intuition and what are the rules uh, when we are dealing with operational amplifiers. So let's see how we can do an integration physically. I mean, these are made of a silicon at the end of the day. The operational amplifier, it's kind of a chip, if you see, and the capacitor, we have operational amplifier here. This is on-amp. This is a chip, a chip. We have some pins here. This is a chip, yes, and we have a capacitor and a resistor. So how integration can be done through these silicon chips? So let's get started. So I hope you have some understanding about what are the uh, things in operational amplifier. So the first rule is in operational amplifier, I mean in an ideal one. So I do this proof for ideal one. The voltages here to the plus and the minus are same. So since this plus is grounded, it is 0 volt, and this is also 0 volt. And you will know that in the ideal operational amplifier, the input current towards the op-amp is 0. That means no current is, there is a current here, so no current flows in towards the uh, op-amp. It is just because if you uh, dive into the inside of a op-amp, it will look like this actually. It will look like this actually. So there is a huge resistance in the inverting input and non-inverting input. So I'm not going to basically talk about operational amplifiers. So I hope you can understand this. So this is inverting input, this is non-inverting, this is a plus, these are supply voltages, this is the output voltage. So if you see that here is 0 voltage, so here is also 0 voltage, and this point is same as this point. This is the out. Now, so the voltage difference between the capacitor is V out minus 0, that is it is same as V out. So voltage across the capacitor is V out. I denoted VO. From the characteristic equation of the capacitor, it's Q is proportional to the voltage. So simply Q equal CV, and in this context we get VO is equal 1 over C times Q. That Q means the integration of the current of time. So this is the characteristic equation that we can use to cross voltage across a capacitor. So here you can see that there is some integration. So since there is integration, we can do some integration through this kind of circuit setup. we supply some kind of input voltage, and with that input voltage the current is changing, and since the current is changing, output voltages is some kind of integration. So how we can connect that V in here? So to see the voltage across this point and this point, it is V in minus 0. That means V in. So if we apply simply Ohm's law, V in is equal I times the R. R means this capacitance over here. So we can simply, in this equation, V out is equal 1 over C integration, that IT means V in over R. So R is a constant. I can get it out of the equation times dt. And there is some kind of interesting things goes on here. That is, actually when I'm getting the out here, I just consider to explain. I just consider the voltage difference is the out. But actually we know that current is the flowing of current is like this. This is the path of current flowing. So this is V in. So IR voltage drop, you come to 0 volt, and here you have 0 volt, and towards this side to this side, that means here voltage is 0, here voltage is V out. So 0 minus V out. So the actual value is 0 minus V out. Okay, 0 minus V out. So V out is minus times integration of V in dt. So this is why we always say that if you put this feedback circuit, the feedback means the output connect again towards the input. So if you connect this feedback capacitor towards the inverting input side, it inverts the sign of the voltage. So you can clearly see that there's a minus sign here. It is happening because this here is 0 volt. The voltage difference is 0 minus V out. The current is flowing this way. The current is here. Current is flowing this way. So it's 0 minus V out. Uh, so the voltage is inverting its sign. So that is about the equation that we got. So here the real magic happened. We have some kind of integration. So now let's see by simulating how this is happening by a silicon to a mathematical integration. So in this simulation purpose, I used LTspice. It's a really good software that you can do uh, simulations. So I have this setup of the circuit just I uh, explained it earlier. Here we have the operational amplifier. It's a standard one, and the minus supply. This is a supply voltage, plus and minus supply voltages. Plus and minus supply voltages. So minus sign of the supply voltage here I connected to the minus 15 voltage. So the values that I select here is the purpose of clear kind of see in the graph. So it's the minus, this is a voltage source, the minus sign of the supply voltage. So plus sign is here connected to the plus 15 voltage. So this is plus 15 and this is minus 15. Here we have the input voltage. I already set some kind of a function here, some kind of a time-based function. I have a capacitor, a resistor here, it's 1K, and the capacitor. So let's run the simulation to see what's happening. So I want to graph this point. This point is simply the in, that you can see it's kind of a kind of graph like let's say it is, you know, for which it takes some kind of m times x, or here it's t, so it's kind of empty. So graph t is equals t, and if I plug this point and this point, look what I get. The blue line is the output voltage. The domain is time domain, and if I integrated my input voltage, which is ft, it is integration some kind of a constant time t. So it is like t squared something. It's a curve. Here I prove that there is a minus sign here, so there is a minus sign should be added to here when we see the output. So it's minus times some kind of square. So you can clearly see in this simulation it is the same as this. Okay, it's the same as this. It's a curve. This is a line. This is a curve, and it is inverted, and it's integrated. That's the most important part. This is the integrating function of this. If you see this simulation, that you can see some interesting facts. The first thing is this is not entirely integrated. After this point, it's cost value. If you see what voltage it becomes const is 15 voltages. So that is, if you already studied about operation and amplifiers, you know that the amplification cannot be overcome the input voltages. That means plus or minus 15 voltages. So clearly the amplification should be inside that plus or minus 15. So it will not be go beyond the minus 15. It's just a flat line, and input voltage is just fine, and the output voltage cannot be go beyond the supply voltages. And this is how a silicon chip make an integration. Now let's try some interesting functions. Let's try this function. I already have some functions. This is a constant sine function. This one, run this again. Oh, what we get? So my input function is look something like this. The the in is equal to the sum const times sine omega t. The omega is also const. So V out should be minus 1 over RC, so it is also the const. Some integration of, let's say, C dash sine omega t. So integration is minus C dash over RC. If you integrate it sine, it is minus cosine omega t times over omega. So these all are const. So it is k cos omega t plus. So there's a plus c here, plus c. So now go to the simulation. Look what we have. Look what we have. What we got is k. Look what we have. In there, you can clearly see that the blue line is a cosine line, but it has some kind of a DC offset. You can see. So if we go to the equation, what we have, it is the equation we have for the output voltage is k times cos omega t plus c. There is a plus c in here. So that is the DC offset. So, so cos function is The normal cost function is something like this: 0 x 1. So when we have DC offset, this offset, okay, DC offset means that here this is coming like this way, it is moving like this way, so it can go to the minus plus. So our input is just a sine wave. So isn't that is what we got in simulation? Of course it should be good. I mean, I wanted to say that interesting facts about mathematics, how it meets in the real world circuits. So here you can clearly see that this is a cosine function that offset, which has a DC offset, and you can also clearly see it. I choose these values because I can. There is no cutoffs, because you can see that it is the maximum minus sign goes here is like minus 1 voltage, so it does not go beyond the minus 15 voltage. So I can clearly see a beautiful cosine wave here. So next we find some kind of very interesting, very interesting function as the input voltage. It is the function is this. Running the simulation. Oh, sorry. Okay, this is the function. The function is, you can see, v is equal exponential means e to the power minus something here. So I choose these values that I can get the equation. I can see the simulation very well. You see, simply this function is something like this. The in is equal to the in is equal to the and some kind of constant at the front. You can see it like k1 times e to the minus t square. This is, if you know already, this is kind of interesting function. The all mathematicians show that the antiderivative or the integration of this function, a function sometimes you can write e to the minus square, it is not possible. They say that there is no solution. But if you run this, if you see the simulation, I mean, the silicon, these capacitors, the resistors, they don't know about mathematics or integration. It is how they behave. But mathematically, this function cannot be integrated easily. So this function is nothing but a bell curve. This is the famous bell curve that you will find in the form of this, in the form of this minus t squared. This is basically the bell curve. This is kind of most some kind of fascinating function that you could find in probability and geometry and kind of things. So, as we expected, the out should be the out should be some kind of const. I know that minus some kind of a const times integration of e minus t squared dt. So if you try it, e to the minus t is it is really easy to integrate, but when it comes to e to the minus t squared, it cannot be a single algebraic form or logarithm of sine or cosine. You cannot express it like that. Uh, uh, let's deep dive into what e to the minus t squared means. If you use the definitions of e to the minus t, you could write this as this. I mean, if you use the Taylor polynomial, Taylor expansion for this, you can see 1 minus t squared over 1 factorial plus t to the power 4 over 2 factorial, and again it's minus t to the power 6 for 3 factorial. I hope you uh, have some kind of intuition about the Taylor expansion. If you are not familiar with it, it's not it's a fascinating mathematics. It's the Taylor's theorem is you can find any function if t that is equal to the summation of k is equals 0 to n f to the kth derivative of this times a is a cost. That means, when we are writing the Taylor series, we writing Taylor series around some kind of value. So we are approximating our function. What we are doing is we are approximating our function through Taylor series. So this const a means around that uh, around that point. We write in Taylor series around that point. If the k derivative times a, so is the const times x minus a to the power k over k factorial plus the Taylor remainder. So this Taylor remainder is, this n is a finite value. So there is always error. So Taylor remainder is the error we got here. So remainder can be written in certain forms. Uh, Either you can write this like, if you had, this is until the end term. So if you n plus 1 to infinity, the same thing comes here also. You get the remainder. So also you can get the remainder as like, you can write it like f to the power n minus f to the, if the n plus 1's derivative of x, f times zeta. Zeta is I will tell what zeta is, times x minus 8 to the power n plus 1 over n plus 1 factorial. So see, this zeta is between something between the x value and the a value. It's greater than a value, zeta, and it is less than the x value. So in this form also you can write Taylor series. Oh, anyway, this is not about Taylor series. So okay, I just made some intuition. So it is, if you haven't learned that, go ahead and learn. It is very important theorem that we could find. So uh, so the basic idea actually in this remainder is, when we are go beyond, you know when we writing our function to some kind of this a value, if you go on beyond this value, so the error becomes higher. So near this const, the error is low. When we go beyond that value, the error is become more. So go ahead and run it. So we are here. So we have our function. So we now we can integrate it actually. Okay, if you integrate the both of sides, so integrated minus t square uh, is actually t minus, t squared integrating its t cube. We have some kind of over 3 here also, 2 times 1 here, so we have plus t to the 5 over 5 times factorial like that. So yeah, so it's infinite sum. So this is, since this is an infinite sum, what we do is we define a new kind of function here. So we have definition of the ERF, the error function f error function x is equal to 2 over root pi integration 0 to x e to the minus t squared dt. So what the hell is this? So actually, to the meaning of this 2 over 5, actually there is a meaning for that. If you integrated uh, this bell curve, this bell curve uh, minus infinity to plus infinity, you would get something like 2 over root. You can do it or not. Root pi over 2. So when we define its function, we get the inverse of this to minimize this. So since that in our case the t is time, for let's say we want to find the output voltage as time at 1 millisecond. 1 millisecond. So you clearly see that the sum is infinite. It cannot be done. So what we do is we don't entirely get the whole sum. We just do is, so if we um, if we get the 0 to x minus t square dt, that is simply ERF x root pi over 2. So what we do is we simply calculated until x terms. So here until x terms, some kind of x terms, we get the sum. So that is what we do. So what I have here is the definition of ERF function. So if you want really dive into the what is our simulation plot, you can see there is the bell curve here, and you get a number kind of nice curve here. So to this curve, we don't have some kind of general equation that we can write here. What we done is using this error function ERF, we calculate it. So if you using some kind of a digital way, actually these are analog systems. Okay, in your computer the integrations and differentiations are not happening in this way, this analog system. But if you use some kind of digital way, maybe it uses some kind of more computational power. But in this point, in this manner, it doesn't know about integration or differentiation, you just get the value. So even though this is some kind of a mathematically important function, we have uh, even though mathematicians say that it cannot be, this integration here it cannot be done directly through it, so we give it a new name and define something new, and here we get something. So what I want you to is search about them, search this about this error function and its uses and kind of things. So let's move some kind of another interesting function. I have some kind of interesting function here. We go down it and we can simulate it also here. Let's see, I get this function. Simulate. Oh, uh, actually the function I have uh, here is something similar to this. It is like t is equal to the sometime a constant e to the minus t sine omega t. So if you plot this, you will get a function like this. The sine wave is some kind of decaying sine wave. So So what is the differentiation of this? Okay. I think it's going to be some kind of different integration class. Sorry, integration. Okay, integration class. So can integrate this. Take a little bit time and try to integrate this. Maybe you should the integration by parts. Uh, I'm not going to do it. It is really easy. You can maybe you could integration by parts twice, because once you do this sine become cosine, and again you use its cosine become sine again, and you can bring that to this side, and you end up with a good solution to this equation, the integration of this. I will write the answer. The integration of this is like in the form of e to the minus t sine omega t plus cosine of omega t. That is constants. Okay, I just write the simplest form. So it is like the same function as this. Okay, only cos term is added. So I graph it using Desmos, but I get this. Uh, but in the simulation we have some kind of several different value, because you know by applying the initial conditions we should find this c. Okay, in default this I set the initial values of the v out to be 0, so you can set this t equal to 0 and make this equal to 0. Sorry, this script. Okay. T is equal to 0 and make that equation to 0, and you can find this c in here. So with that c, if you graph it, it should exactly look like this. So it's the same kind of function but inverted. There is a minus sign here, it is out. It's kind of minus sign in here in dt, minus there is also rc here. So I made it where is it? This minus sign. V out is equal minus times rc, the integration of v in. So because of that minus sign, this becomes inverted. So that is what I wanted to tell, how this integration and differentiation happening. I just saw that differentiation, it is also some kind of this circuit. So what you have to do is remove this capacitor here and it place it in another place that you could find a differentiation. Uh, so what are the uses of this? So what is the use of this? The main use of this is kind of like P PID controls. Uh, let's say that you are working on a lab, and the temperature of that lab is important factor to security info, security standards, or the quality of the product. So there is some kind of way that you measure the temperature, and you can generate some kind of voltages with that temperature. So let's imagine that there is a standard temperature. So there is an error happening. The error happening T set, PID controls T set minus T T at the not that this means at time T what is the temperature. So this is kind of error. Okay. So what do you think is like this? If there is a difference, there is an error. So you have to overcome it. So there is, we said UT. So there is some kind of component that continuously look at the temperature differences and make it correct into the correct temperature. So it's Ki times the error at the time t, error at the time t. So yeah, it is fine, but there is a problem. Imagine if the time you will see that temperature is all good, but it suddenly goes up. So, so I mean, this like it suddenly goes up. It suddenly goes up. Maybe that sudden goes up. Maybe have a very dangerous impact. So what we do is to this correct this is the correcting. To this we are adding the differentiation of the of this error. Also dt. So if you going to make this also through this proportional concept, it will not going to work because this is the future. I mean, this is like when even for a small change, when there is a big change in the function et, it suddenly understand that this is going to be really dangerous in future, even though there is no much change in the uh, et value. Okay, there is not much change in et value, but it is going to be a big problem. So it is going to be a big problem. So even though this et is slow, it is low for this kind of range, but the slope is really high. So this is a really needed uh, measurement to correct the temperature and warm. And what's happening if something like this happens? Take this got right, okay? This would correct it. See something like this. The it is not changing much. You can see it is changing a little bit, little bit, little bit, little bit. But that little changing over a big period of time. So how to understand this? What you should do is you should add differentiation, integration, integration of the t over time. So over time, if this becomes high, that means uh, this can understand easily if there is a small deviation, a small error through a long period of time. So this is like looking at the past. This is looking this tells the future. This tells the present. So in a practical scenario, all these terms are needed for a better correctness of the temperature. If you are only just looking at this term, this is really wrong. I explain you to a small et, even if the slope is really big, it is going to be a really big problem. So this term is really needed. And also, if there is a small change over a really big period of time, we should investigate and we should understand that. We could warn that also. So this term here is also really important. So small change, a really big period of time. So that it means PID controls. Proportional. This is proportional one. This is the differentiation one. And this is the integration one. So this is to some kind of this circuit. Maybe you can use uh, analog op-amp. So that is a use case of this op-amps. So, we are going to wrap up for today. So we spend some time today, right? I mean, in today's world, we writing digital codes, loops, arrays, and discrete logic. That is easy to forget what computing actually is at its core. I mean, today we did write a single line of code. We didn't use CPU or clock cycle. We just arranged a few pieces of silicon, resistor, and a capacitor, and the laws of physics to calculate impossible calculus in real time. The digital computers are undeniably future because of their flexibility and precision, uh, rather than analog systems. But there is an absolute elegance in the way that analog computer force into the universe to do math for us. So I I welcome you all to the use these things using simulate these things using LTspice, spice, and you can do your own things and do some kind of experiments, some maybe some root functions and maybe some kind of practical scenarios in these analog systems. So if you enjoyed exploring physics behind the code, you can stay with the channel. So this is my first video, so maybe there is many issues. So sorry for that. I think I can improve your future. So goodbye for today.